And another good day for metamorphic petrology. We're going to wrap up our introduction to the topic by going into the different agents of change. Now, some of these are not going to be very new to you. And in fact, this is a bit of a review. So we're going to need to go through how temperature and pressure change throughout the Earth. That's the geotherm and the lithostatic gradient. So it seems a bit redundant, but it is a great opportunity to emphasize things of high importance. So temperature is important to metamorphic reactions because with that increased temperature, what we have is a situation with increased energy, which causes bonds to break. All right, that's the breakdown. But then, of course, new minerals can form. So let's go bonds to break and then reorganize into new minerals or new textures of the same minerals. Underneath temperature, we need to, of course, recall the geothermal gradient. Recall the geotherm. What is the geotherm? Well, generally speaking, we say that the geotherm in normal tectonic areas is 25 degrees C per kilometer. So if we were to graph this, we can have pressure here and temperature here, and kind of shooting through the middle of the graph is what we would say would be the norm at 25. But there are many other different geologic environments that could have different temperatures and pressures. We could have really cold environments that might have 10 degrees C per kilometer. And there could also be warm geologic environments, right, where the temperature increases very fast but pressure does not, that get up to 40 or 50 degrees C per kilometer. And so what we need to do as we think about the geotherm is we always need to be considering the different tectonic environments that can cause warmer or colder geotherms. Things like a convergent boundary with a subduction zone could be colder, and something with a in fact, we could even do this, like convergent would be cold, and we could say an extensional environment might bring mantle closer to the surface or make more magmas that could be hotter than normal. There's also magmatic environments that are going to always be hotter. There also can be considerations about the age of the crust. Really old crust has had an opportunity to cool more than younger crust. So all of these different factors can influence the geotherm. The next thing we should consider as our agent of change is pressure. Pressure. The type of gradient we're concerned with here is the lithostatic gradient. I guess we should put a definition of why pressure matters first, even before lithostatic gradient. But what we're going to say here is that increasing pressure causes mineral structure to rearrange and form denser phases. So let's say that increasing pressure causes mineral structures to rearrange to form denser phases. One place where we saw evidence of this non-metamorphically was in the mantle, as olivine goes to Wadsleyite, goes to Bridgmanite, right? As that Mg2SiO4 lattice gets more dense. Now, in terms of what lithostatic gradient is, we tend to think of the lithostatic gradient as 1 kilobar equals approximately 3 kilometers. And that relationship allows us to graph this as well, where we could have pressure relating to some depth in kilometers. And the lithostatic gradient, it would be here, where the slope of this line is equal to rho GH. And rho, for most of the continental crust, is around the same, right? Maybe 2.7 to 2.8 grams per centimeter cubed. And so that's our normal situation. But if we had rocks like basalts that were more dense, then pressure could go up faster than normal. This would be something like a basalt, a mafic rock. You could have a steeper than normal lithostatic gradient, or you could have a sedimentary system with a lot of porosity that could have a lower type density. Maybe a pumice would be another type of situation that would have a lower than normal lithostatic gradient. The range for metamorphic rocks is usually less than 12 kilobars. Why is that? Well, 12 kilobars, what does that equal? That's about 36 kilometers using our normal geothermal or lithostatic gradient, and that's about where the base of the continental crust is normally. All right, and so metamorphism is going on within the crust. Now there are some environments where the crust actually can go, let's put this down, UHP. That stands for ultra high pressure metamorphism. And this is the type of metamorphism that is going on in like the keels of the world's largest mountain ranges. It's a pretty interesting topic right now for scientific research. And so this is where we have over thick continental crust, CC. We often do CC for continental crust in geology. Now one thing of course to always remember, we'll put a star here, is that T and P go together. And that's what allows rocks to change with these repeated facies that we see along the earth, around the world. And so because T and P go together, we can say that they produce predictable petrologic relationships controlled by tectonics. Right, that's kind of one of the big themes of metamorphic petrology. Now there's two more types of agents of change, and let's get into those right now. These are maybe a little more new, although they'll seem obvious to you. The first is going to be stress. There's a lot of stresses involved in tectonic collisions and extensional environments and deep in the crust. And let's put a couple bits of information down. One, what is stress? Well, stress is the force applied. All right, applied to a rock. That's what we think about when we think about what is stress. Then the response to stress is strain. So let's say strain is response to the stress. What does that mean? Well, it's the deformation. It's the change in rock textures that is produced. We have a variety of different types of stresses. There's three. There's tension, compression, and shear. And what we're going to start is with, this is going to be our generic first shape. It's supposed to be a cube, all right? Or just let's have it be a square. And we're going to deform that square with these different types of stress. So in the tension, well, you know what happens with tension, right? Tension is our stretching stress. And so what will happen is we will have that cube will get stretched into a rectangle with the primary stresses like this, pulling it apart. And then there would be these minimal compressional stresses. That is opposed to compression, which is our flattening stress. And we could take our square and we could compress it very, very much, and we would get a rectangle. All right, because here is where the maximum compressive stresses, and then we have these minimal extensional stresses. Notice the shape is exactly the same, but the force and the force direction and the type of stress is totally different. And so we have to be have other clues in order to infer which is which. So let's say that to infer cause, because shape is same, we must look at other clues. That's pretty sloppy penmanship, but you get the idea because I just said it out loud to you. Another word for this compressional stress, when it's caused by gravity, is called the normal stress. Oops, not normal, not two L's. This is when it is a gravitational compression. All right, and then the last type of stress to get into is shear stress. Let me give you a definition for shear stress. I think this is a really nice simple one. It's called lateral differential stress. You can see it really well with a deck of cards. You take a deck of cards and you push along the top of it in a direction, you'd get that deck of cards to move laterally. So another way to say this would be material moves sideways relative to the neighbor. Let's just say that material moves sideways. What does that look like with our square? Well, with our square, we'd have this going on. Here would be how we draw the arrows for the stress, and the actual response of the square would now be to make a parallelogram. So what I want to head to next now is this just idea that kind of wraps all of the stresses up together, and that is that the minerals are going to respond with different deformation textures. So minerals respond to tension, compression, and shear with different textures. That's going to set up our next lecture. But mechanistically, how does it do this? Well, let's have this be number 7. This will be called our mechanisms of response. There's 2 main mechanisms of response. One is called dissolution and reprecipitation. So dissolution occurs at the high pressure points, and reprecipitation occurs reprecipitation occurs in the low stress areas. So let's say this, we'll go dissolution at high P zones, and reprecipitations occur at the low pressure zones. What would this look like? Well, here's our original square. It is being compressed heavily on the sides. Well, dissolution is going to occur here on the sides, all right? There's our dissolution. And our new growth is going to occur here, where there's the lowest amount of pressure. So that will be our growth. That is our number 1 mechanism. And then the second mechanism is called plastic deformation. Because remember, this is all happening in the solid state. This is a tricky thing to have happen. But crystal lattices can plastically deform in response, and I guess the response would look like ductile flow. Now, this is not exactly what it's like, but like logs aligning in a river would be one way to picture how plastic deformation and ductile flow could work. So those are our 2 mechanisms of response. And then to wrap up the lecture, we do have one last agent of change. We've talked about it a little bit earlier in the semester. We might have used a different word for it at the time. It's called metasomatism. Metasomatism really means hot, well, it has to do with hydrothermal fluids. So let's say hot hydrothermal fluids infiltrate a rock. Infiltrate rock and cause chemical change. This is very common in a number of different environments, but the main thing that this produces are veins. It can be veins of metamorphic minerals or veins of ore minerals. So let's just, like, if we have veins of ore, like gold or galena, you can have veins of minerals like epidote. That would be a metamorphic vein. You can have low temperature metamorphism, produce veins of quartz. And to just kind of make a couple quick sketches here for what this looks like. So here's the surface of the earth. There's some trees. Let's say we have a magma chamber in the subsurface. Okay, there's our pattern for magma chamber. Well, you can have hydrothermal fluids being released from the magma chamber, or you can have groundwater circle down and get heated. Both of these situations will produce hot hydrothermal fluids that can alter the rock and produce, veins of minerals. The other environment is the subduction zone environment, where, let's see, how do we do this? We're going to have, here's our waves. Well, we can have dewatering reactions occurring off the plate because minerals are no longer stable in the pore space at the shallower depths. So this would be pore space water. Or here, it actually could be lattice-bound water. Well, neither of them become stable, and then you get hydrothermal fluids either percolating into the mantle or into the overlying crust or even along the interface of the plate. These would be places where you have metasomatism metamorphic reactions. All right, that's it for the intro to metamorphism. See you next time for kinematics.